Hello, I am firdose. It is a small topic about a combinational logic circuit and its design. It is from the digital electronics. Logic circuits basing on the applications based on the requirement. It can be classified into two types of circuits: combinational logic circuit and sequential logic circuit. Before going to this, we know about what is the logic gates. So logic gates perform a basic logical functions. They are fundamental building blocks of the digital integrated circuits, which can allow us two binary values and outputs of a value of zeros or a ones. The given inputs can be in the binary. The given outputs will be in a binary in a logic gates. There are different types of the logic gates in there, which is basic logic gate. Second one is universal logic gates. Third one is exclusive or automatic logical gates. So here in the first one basic gates. First one it will be a not gate. Not a gate generally inversion of the given input, reverse of the given input. Okay, given by the input 0, we're getting the output as 1. If we give the input as a 1, then output become a 0. The second basic gate will be OR gate. So here OR gate, the output expression will be y. Y will be an output variable. Then inputs are x comma y. Output as a y is equal to a plus b. It is a addition of the two input variables. Third gate is a AND gate. Here in the AND gate, the inputs are the same. There are two inputs there where output y is equal to a dot b. Product of the given two inputs are in the AND gate operation. We know about NOR gate. NOR gate expression y will be a output, then y is equal to the inputs are x comma y, where y is equal to a plus b whole bar. It is a inversion of OR gate. Next gate, NAND gate. Here in NAND gate, it is a reverse of AND gate, where y is equal to AB whole bar. So AND or NOT gate are the three basic gates. Why it is named as a basic gate? By using these three gates, we can make any type of the gate. The last, it is a XOR gate and the XNOR gate. So these two are the exclusive gates. So these all are the logic logic gates. So the combination logic circuits are a basic building blocks of logic gates only. So what is the basic definition of the combinational logic circuit here? The combinational logic circuit whose output can be depending on the given input only, given a present input only. It cannot be depending on any memory element. The output can be y depending on the present input only. Here in this block diagram, the inputs are x variable x, the output variable will be a y. So they are a combinational logic circuits. Those are adders, subtractors, multiplexers, demultiplexers, decoders, and encoders. These all are the combinational logic circuits. all of the combination circuit. Here the first one is the adder. We know what is the adder. Adder means it is the addition of the two binary bits. We go to addition for the two binary bits. The outputs are sum and the carry are the two out bits. This adder, it is also one of the combinational circuit that can perform the addition of the two binary bits. So it can be named as an half adder, whereas the outputs are the sum and the carry are the two outputs for a half adder circuit. So here the inputs are A comma B. For the two inputs A comma B, we are getting by the sum and the carry are the two outputs. For A comma B, two input have how many possibility here? Four possible outputs. For the two inputs 0, 0, 0, 1, 1, 0, and 1, 1 are the four possible outputs with their sum and the carries. Sum will be at the 0 and 0. Adding up the two binary bits, sum is equal to 0, carry is equal to 0. Adding up the two input bits 0 and the 1, sum is equal to 1, carry is equal to 0. Again, addition of 1 and 0, sum will be 1, carry become a 0. Addition of the 1 and 1, sum is equal to 0, carry is equal to be 1. So here it is a truth table for a half adder. By using this truth table, we are going to generate a Boolean expression by using the Karnaugh map or a K-map. The expression sum is equal to A XOR B for the values 0, 1, 1, 0. Here, applying by the two variable K-map, 0, 1, 2, 3 are the 4 bit for a two variable K-map. Values 0, 1, 1, 0. We're getting the Boolean expression as a B bar plus a bar B, whereas S is equal to A XOR B. Same as for the K map for the carry is double triple 0, 1, where C is equal to A into B. So the XOR B carry is equal to product of C A into A dot B. A and B. So by using the sum and the carry, the logic diagram will be by using the NAND NOR or NOT division. The diagram will be like this. By using the only the NAND gates, the circuit diagram will be like. So for the representation of the given expression by using the only the NAND logic, here S is equal to A bar B plus A B bar. So for this expression, we go for a Boolean algebraic functions. Here we go for a by using the axioms of a Boolean algebra. By using a here by using the De Morgan's theorem, where in the De Morgan's theorem, AB bar is equal to AB whole bar is equal to A bar plus B bar. Again, A plus B whole bar is equal to A bar dot B bar. The Boolean algebraic class and the Boolean function by using the axioms and the theorems, we can be written as sum is equal to B in the NAND logic format. Only in the NAND gate representation, it can be getting by this Boolean expression. Whereas a carry is equal to A, product B is equal to by using only the NAND logic AB double bar is equal to B A, comma AB. C is equal to AV double bar. And is equal to B. So it is a circuit diagram given carry which can be represented only in the form of AND gates. In NOR gates, sum is equal to A bar B plus AB bar. Only in the NOR gate representation again we go for a Boolean algebraic laws and the Boolean algebraic theorem. So it can be again implemented as in the summation of the inputs. That means only in the NOR gate or representation. So here sum is equal to in the only in NOR gates addition of the two inputs A comma B can be represented as a NOR gate of sum and the carry. C is equal to A bar plus B bar whole bar. Here again carry can be represented in the NOR gates. So sum and carry which is in the NOR gate representation. If you want to be in the simple logic diagram for the half adder circuit, simple logic diagram for the half adder where sum is equal to A XOR B, carry is equal to A dot B. Here the product of the two inputs we want a AND gate. Here S is equal to A XOR B means we need a XOR gate. By this we need one XOR gate and one AND gate. For the sum by using the XOR gate A and B are inputs. Sum is equal to A XOR B, whereas carry is equal to A B. So it is a basic block diagram. So for the half adder, generally why it is a name as a combinational circuit means the addition of the two bits it cannot be required any previous bit. Whereas in the sequential circuits, it cannot be. That means the output not only depending on the present input but also the previous output depending by the sequential circuit. Whereas in combination circuits, output can depending on the given inputs only, but in the sequential circuits, output can be depending on the present input and the previous output. So it is a memory element in a sequential circuit. For example, in the counters, it can be counted by use the previous bit because it can be count from 1 to 3 and so on. That means getting the present bit you can have depending on the previous bit also. Whereas in addition of the two bits, zeros and the ones, 0 and 1, it become a 1. So it cannot be depending on any previous output. You just having the given input 0 and 1 the inputs we are getting the result as a 1. So the example will be for a combination circuit will be a addition of the two bits. The best example for the sequential circuit will be a counter. So whereas in counter I can count by using the previous bit only. If you go for the third bit, it can be go for a second bit, 1, 2, 3 and so on. So the counters will be a sequential circuits which output can be depending on the not only the present input but also the previous output only. So the half adder, the sum and the carry are the outputs here. Coming to the full adder it is also a combination circuit. which can add the two binary bits and a one carry, where we get the output as the same as a sum and a carry outputs. The full addition of the two bits and the carry from the previous column. That means for a full adder, it is the addition of the three binary bits. Here the inputs are A, comma B with the carry in. That means carry input C in having the three bits. For a three bits, 2 cube is equal to B8. 2 cube is equal to 8 means there is a combination of the 8 outputs for a given 3-bit input. Again, the outputs are sum and the carry. Sum and the carry are the two outputs. Here 0, 0, 0 to the triple 1, 0 to the 7, having the 8 combinations. The addition of the 0, 0, 0, 3-bit input. Whereas in 3 inputs, it's sum and carry are the block diagram shows A, B, C are the 3 inputs with the respective output sum and the carry. Here 0, 0, 0, adding up the 3 bits sum 0, carry 0. Again 0, 0, 1, sum will be 1, carry, there is no carry, that is 0. For 0, 1, 0, sum will be 1, the carry is equal to be 0. Again for 0, double 1, sum 0, carry will be 1. 1, double 0, sum is equal to be 1. There is no carry, 0 carry. 1, 0, 1, sum is equal to 0, where carry is equal to here 1. Double 1, 0 with 0 and 1. Triple 1 will be sum is equal to 1, carry will be 1. It is a truth table for a full adder circuit. Here the instead of addition of the 3 bits, we are adding addition of the 2 bits, we are going to add by the 3 bit with their carry out, with their carry input. By using the truth table, sum and the carry, sum is equal to B. The values is 0, double 1, 0, 1, double 0, 1. By using this variable, we go for a 3-variable K-map. 3-variable K-map, we're getting the 8 bits. So here by the Carnot map, we can getting by the Boolean expression as a sum is equal to A bar B bar C in plus A bar B C in bar plus A B bar C in bar plus A B C in. By using these values, we are getting the 4 individual cells. By the individual cell, we are getting by this expression sum. Again, we are using the 3-variable K-map for the carry, whereas in carry, C out is equal to AB plus BC plus C in. That means C will be carrying AB plus BC in plus AC in. Carry out is equal to B. The sum and the carry, by using this Boolean expression, we go for a logical diagram for both. Here, the logic diagram will be S is equal to where carry is equal to sum is equal to will be the logic diagram which can be in the AND gate and the OR gate representation, where sum is equal to where carry is equal to in the representation of only in AND gates and the OR gates. In the full adder, by using the two half adders and one OR gate, how can it will be represented by the by using the Boolean algebraic, by the axioms and the laws, by the minimization of the Boolean expression, we are getting as sum is equal to A XOR B XOR C, whereas carry is equal to AB plus C into U XOR B. Here, the full adder, which is the form of two half adders and one OR gate. Here in the circuit diagram, it is a one half adder. It will be another half adder, whereas in a extra gate, one OR gate. By this expression, we are going to make our full adder by using two half adders and one OR gate. It can be represented as by this A, B, C with one half adder, another half adder, two half adders with one OR gate. Whereas output we know as it is the sum and the carry are the two outputs. So it is a full adder by using the two factors and one OR gate representation. So it is all become about the full adder circuit, whereas in half adder you have adding of the two bit, addition of the two bits, whereas in full adder instead of two bits we're going to add some extra carry C out, getting by the inputs as a ABC, same outputs as sum and the carry. Again, by using the truth table, we are going to make a K-map. By the K-map, we are getting a Boolean expression. We know by the expression we make a logic diagrams. It's a logic circuit diagram. Again, how to represent a full adder by using two half adders by the OR gate. We go for the Boolean algebraic functions by the laws and the axioms. So we can again represent the sum and the carry by this. Again, here the subtractor. We know the subtractor, that means whereas in addition of two bits, here we can subtract the two binary bits. But subtraction we are getting the difference and the borrow and the two output variables. We subtract the one bit from the another bit to produce a difference in the borrow output. Also, as an output specified by the one has been a bar. Here, the subtraction of the two bits is 0, 0, 0, 1, 1, 0, 1, 1. So these are the four possibilities by the two input variables 0, 0, 0, 1, 1, 0 and the 1, 1 are the inputs, whereas in D and B are the outputs, difference and the borrow are the two outputs. So it is a half subtractor block diagram. A and B are the inputs, so difference and borrow are the two outputs. So we are getting by the D is equal to, so with the subtraction we are getting the DB, but 0 and 0, difference 0, borrow 0, 0, 1, difference 1, borrow 1, whereas 1, 0, difference 1, for there is no borrow, for 1, 1, difference 0, there was no borrow. Here we are getting the borrow by 0 and 1 option only. D is equal to 1, where B is equal to B 1. Difference 1 and borrow 1. It is a truth table for a subtractor. By the truth table, we make a K-map. That means we get a Boolean expression by using this K-map, where D is equal to AB bar plus A bar B. Borrow is equal to A bar B. Here A bar B plus AB bar is equal to D equal to A XOR B. B is equal to A bar B. So it is an expression for D is equal to AB bar plus A bar B. By the expression, the logic diagram will be A and B are the inputs, so D and B are the outputs. where D is equal to V A XOR B, we are using by the XOR gate D equal to XOR B. Here B is equal to A bar B means here by using the inverter we are getting the A bar, just say input B, product with the AND gate, using the AND gate where B is equal to bar O is equal to A bar B. The gate can be, same expression can be represented in the form of the AND or AND not as like this. So this is about the half subtractive. So this is one of the combination circuit we can now discuss here. Addition of 2 bits are half adder. Addition of the 3 bits are full adder. Addition of the 2 binary bits will be a subtractor.